Good day, ladies and gents. Welcome to this talk. We're going to be looking at As Africa Burns, Can We Engineer a Safer Future? I'm going to be running through the physics and engineering aspects of fire safety and applying it to everyday life so that we can see how to make our continent, our homes, and everywhere else safer. So firstly, just an overview of the talk this evening. I'm going to be looking at As Africa Burns, painting a context, painting a picture of what we're currently experiencing and how fires are affecting us. Then looking at the physics of fire. Often fire and fire behavior is misunderstood, so many interventions are not suitable because of that. So we're going to be then going on. Then we're going to apply what we've learned to some interesting problems. Firstly, if I leave a bottle of hand sanitizer, which is almost pure alcohol, in my car on a hot day, could my car catch fire? Then wildland fires. If I live near a green belt, some veld area, some forests, how likely is it that my home may burn down soon? How likely are we going to see large fires decimating entire suburbs soon? Then looking at fire safety in modern construction, there are many innovations. One of the big ones has been eco-bricks. All sorts of places are creating homes and structures out of 2-liter Coke bottles filled with plastic. How safe are they and how can we make them safe? Then looking, another intervention, fire retardant paints in informal settlements. Do they work? And through looking at these aspects, we're going to sort of study how you would apply physics to real-day life to make our lives safer. But firstly, As Africa Burns, whether we like it or not, fire is affecting every part of our life in all sorts of spheres. We've got the Charlotte Maxeke Hospital, the old Joburg General Hospital, which experienced a major fire, caused large-scale evacuation. Then there's the University of Cape Town. Recently, the Jagger Library and other structures were affected, and tragic loss of many priceless artifacts. Same, Stellenbosch University, we've also experienced many fires and lost a number of buildings. Imizamo Yetu, Hout Bay, 2,000 homes destroyed in one incident, and there's been numerous other incidents. I mean, there's over 5,000 informal settlement fires a year. Knysna, 1,000 homes destroyed. Kendal Power Station, significant damage. South African riots in 2021, many businesses and warehouses totally gutted by destructive fires. So what do we start doing with them, and how do we start dealing with them? Are these just acts of God that nothing can be done about? Or can we engineer something to deal with them? So this picture now, looking more broadly at Africa, the talk focuses very much on South Africa. However, everything you see discussing here is occurring in the rest of our continent in lesser or greater degrees, and normally in greater degrees. Now, this picture you see on your screen is fires that occurred in 24 hours. And these were fires that were big enough to be detected by satellite. And you can see there are hundreds of fires on a daily basis across our continent. And this was taken during the wet season in the Western Cape. So you cannot see very few fires down the bottom of the country. But in the dry season, you'll see many more orange dots all across the Western Cape and other parts of South Africa and Africa. So there are ongoing numerous fires occurring, costing millions, creating large amounts of carbon dioxide emissions, and a major problem we have to deal with. Now, let's think about Africa as a whole. We've got all sorts of infrastructure projects on the go, whether it be energy and mining and transportation and water and et cetera, et cetera. But if we have a look at a couple of key factors, firstly, our increasing population. Our population in 2017 was about 1.2 billion on the continent. That's estimated to increase to about 2.5 billion people by 2050. So our population is going to roughly double in 30 years. That is a lot of people we have to accommodate, provide jobs for, provide homes for. And combined with that, we have urbanization. So now we've got people moving into our cities, making the problem even worse. Now we have more that we have to deal with. Bigger cities, dense cities, the likes of Lagos and Johannesburg are going to have to deal with very dense, poor, challenging circumstances where fire becomes a significant problem. So let's have a look at some statistics now. These are the number of fire incidents and the number of fatalities in South Africa on the left-hand side, and the number of reported fire incidents in Ghana on the right. The main thing to note is that there's a progressive upward trend. The number of fires is increasing every year. We have more fires than the year before. Now, initially you say, well, that kind of makes sense. We have a growing population. But to put this in perspective, let me show you the statistics of the developed world. This is the number of fire incidents per year in the USA. And you can see there's a progressive decrease from around 3 million incidents in 1980 to about 1.4 million incidents in 2020. So there's less than half the number of call-outs to fire departments. Same thing with England. From around 1 million call-outs at their maximum, they're down to about 500,000. They're actually closing fire stations or scaling back rather than opening. They are winning the battle, we are losing the battle. And what's even worse, if we have a look at our statistics to flick back, our statistics are not complete. There are about 63,000 reported incidents per year. This was the 2020 statistics, but many municipalities are not even submitting statistics. Cape Town has over 22,000 recorded incidents per year, but yet Johannesburg has 1,300 or almost 1,400. Tshwane has 3,800. You can see that just doesn't ratio. If we used Cape Town's statistics and applied them per population to the rest of the country, we would have 320,000 fires rather than 63. So the truth is somewhere probably not that high, but we are significantly underreporting. We maybe have 150 or 200,000 call-outs per year that we're paying staff for, fire departments for, trucks for, and then also just the major damage, insurance losses, and the likes. So moving on, coupled with our growing population and our increasing number of incidents, we also have poverty, major challenge. If you have a look at this graph showing the number of people in extreme poverty in the world, you'll see sub-Saharan Africa is the one place we are not winning the battle. South Asia, East Asia, various other places in the world, they have less and less poor per year. We have more and more, which we have to deal with. So now, the new Great Fire of London. If you look internationally, many big cities have experienced the sort of fires we now see on our doorsteps. London, Istanbul, Tokyo, Chicago, New York, Lisbon have had large-scale fires wiping out entire sections. But over a period of many years, they've progressively decreased the number of incidents, decreased the size of incidents. Sometimes this has taken 50 years, sometimes it's taken 200 or 500 years, but they are winning the battle. The same big fires we see on the right-hand side in Imizamo-Yethu, which destroyed 2,000 homes, look somewhat like the Great Fire of London on the left-hand side. So we can follow suit. The question is, are our resources growing fast enough for us to be able to deal with this problem? Furthermore, let's see, have we learned our lessons? About 100 years ago in the USA, there was a major incident, the Triangle Shirtwaist Fire. 146 people died in a garment factory manufacturing clothes. Doors were locked to keep people inside and keep from stealing. Various things happened. They got trapped and died. And it led to the formation of many codes and standards that have helped improve fire safety in our communities. Now, move 100 years later, you've got Bangladesh, a garment factory. Same thing happens, except this time was 1,129 people dead 100 years later. So in the developing world, we haven't necessarily learned the lessons the developed world has. We need to start implementing the requirements to put these things into practice. So let's now move on to the more interesting part. Let's have a look at the physics of fire, and then from that we can learn lessons to apply to all sorts of weird and wonderful problems. Firstly, taking you back to school, fire needs three things: heat, fuel, and oxygen. The heat heats up the fuel and the oxygen, and once there is enough heat applied to your fuel, the fuel becomes a gas, pyrolysis, so only gases burn. Solids and liquids first become a gas, and then they can be ignited, combined with oxygen, and they can burn, and then your fire occurs. And then also there is a fourth aspect to the triangle, so often it's called the tetrahedron. We need a chemical reaction. If we can stop any one of these 3 or 4 processes, or stop them from being present, we can stop a fire. So that's the basis for some of the things I'm going to discuss just now. Can we remove the heat? Can we remove the fuel? Or can we remove the oxygen from a fire? And we can stop it. Now, here you'll see an experiment running where this item is being tested under a heat flux, and you'll see gases coming off of it. And once there are sufficient volumes of gas then it ignites. There's a little igniter going tick, 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 sparking onto it. And then this is how you would test a material. It's called a cone calorimeter at Ignis testing. And you use this for understanding materials. But the important thing there was radiant energy applied to a sample. The sample progressively heated up. Enough gases came off. Once there was a sufficient concentration of gases and they were hot enough, there was igniter and igniter, and then you got sustained burning. So all the fire triangle aspects were present there. So now let's apply this on a bigger scale. This is the stages of fire development. So a fire starts, you need an ignition. You need a spark, an electrical fault, arson, whatever it is, some sort of ignition causation, some sort of initial event. Then the fire slowly starts growing. There's the growth phase. And then we get into what's called flashover, where the fire was burning a couch. The hot air is rising to the roof. The hot air layer builds up to a point, and that hot layer at the roof is radiating heat down on everything. And then you get flashover, where that radiation is enough to suddenly cause everything to ignite. There's a rapid increase in temperature, and it goes to fully developed. Then it is limited by the amount of oxygen entering the dwelling, and then you go into decay as the fuel is consumed. So here you will see a flashover event occurring. So this dwelling, you can see there was a sudden transition between fire at the bottom on the fuel, where suddenly then everything was in flames. Now let's put this together again on a large-scale experiment. So I'm going to show you now 3 informal dwellings in a row, timber clad on the outside with timber on the inside. And this was part of a large-scale experiment to study fire spread. And the dwelling on the left-hand side, there's some timber cribs, some timber at the bottom burning away. The temperature at the roof, you'll see in the top left, slowly rising. And then now suddenly it's touched the cardboard around the sides, and now you have flashover as the cardboard around the sides is ignited. Everything in the room then ignites, and then it spreads onto the next dwelling. The next dwelling then undergoes ignition, spreads into it, the hot layer drops, everything in the room ignites, spreads to the third one. At this stage, we had a 3 to 4 meter diameter fire whirlwind forming because of the intensity of the fire. And then, as you see now, the third dwelling on the right-hand side, it is now starting to be ignited, rapid flashover and continued spread. And at this stage, the first dwelling is already starting to burn out. It's burned through the walls and then will collapse shortly. Temperatures of almost 1200 degrees Celsius recorded. Very severe, very intense. But that just showed you the steps, the phases of an enclosure fire. Now, coming along, how do we apply this physics? Well, I'm just going to do a quick case study looking at where physics should be applied. So this, for instance, is a LinkedIn post, seems to be by a well-known person looking at a fire safety device. And what's interesting, there are 48,000 likes on this, lots of comments, and almost 1.8 million views. Now, this is what it shows. There is a device, throw it into a enclosure, and then basically the devices blow up, and then the fire cuts out. Yay, looks very impressive. And these are then marketed to municipalities, to companies, etc. But let's start applying the physics now to it. So here we have an enclosure, we have fire, we have a suppression system. Now, those balls contain what's called dry chemical powder. So it's meant to blanket the fuel and prevent more fuel from coming off. So you cut out the fuel. And if you have a distinct pan, so if you have a square or circular pan of fuel, petrol or hexane or something burning, it can blanket it and stop then the gases from coming off. So that you'll see in the top right. However, what happens if it's a more complex dwelling? What happens if it's got beds and chairs? You throw it in, it blows up, the fire's quite well developed, and it just deposits all over. If it doesn't blanket everything, there's still pyrolysis gases coming off, and it still keeps burning. And also, if it has no cooling effect, then everything is still above ignition temperature, so it just keeps burning as gases come off. So we tried this sort of product for, let's say we wanted to use this in informal settlement. So we built a dwelling, set it on fire. I enjoy my job, and then we started throwing. I was very impressed. We didn't miss once. We threw 12 of these balls into the dwelling, and that's shown in the the red box. So that's a time temperature curve. You will see now that there were 12 balls thrown, sometimes 2 at a time. Nothing happened in terms of temperature. 12 balls at around 600 Rand each went into the dwelling. They didn't slow the fire down at all because it wasn't blanketing all the fuel, and there's so much turbulence, the dry chemical powder got moved off the fuels and ended up on the floor, so it didn't stop the fire. Now that we've discussed some of the physics of fire, let's have a look at some applications. The first one, almost slightly amusing: can my car catch fire, burst into flames, if I leave a lot of alcohol hand sanitizer in it? Because we do know that alcohol burns and burns very well. And so we've all been carrying around with COVID bottles of hand sanitizer in our cars, or people have handbags, etc. But now you will see videos like this on the internet where it'll say, this was someone's car, it was left in the sun on a hot day, and then just suddenly burst into flames. So let's start testing and seeing, is this true? And is this something we should be concerned about, especially if you come from Uppington or Paarl or one of these really hot places? Could this happen to your car if it gets 50 or 60 degrees inside? Now, there are a couple of concepts we first need to consider. Firstly, flash point. The flash point of a liquid is the minimum temperature at which the liquid gives off sufficient vapor to form an ignitable mixture with air near the surface of the liquid or within the test vessel used. So alcohol's flash point is normally around 1 to 6 degrees Celsius. So if you have a volume of alcohol and it's about 1 to 6 degrees Celsius, you can ignite it immediately above, and normally have a flash. That's where the name flash point comes from. Often burning is not sustained, sometimes it is, but there's a flash and then maybe the flash is gone, maybe the liquid keeps burning afterwards. But you need a spark or a flame to ignite it. Many people confuse flash point and auto-ignition. Auto-ignition is self-ignition and sustained combustion. You heat something enough that it ignites on its own. And auto-ignition temperature is in the region about 360 degrees Celsius for alcohols. So that was how hot you would need to heat your car to before they spontaneously ignite. So even if you live somewhere really, really, really hot, you're not going to get temperatures of 360 degrees in your car. But also, let's have a look at a couple of other things. You get the lower flammability limit. Now, earlier when I showed you the ignition under the cone calorimeter, there were gases coming off. And you need a certain concentration of those gases before the mixture becomes ignitable. And the lower flammability limit measures that. And for instance, it does range between alcohols, but ethanol you need about 3.3%. So of a volume, about 3.3% needs to be of the liquid, of the vapor coming from the liquid. And so then you can get your Bucky lower flammable limit. This is the volume of hand sanitizer you need to spill in your Hilux for the lower flammability limit to be reached. And depending on the size of your Bucky, whether it's single or double cab, etc., you need to spill about 150 liters of hand sanitizer in it for the entire cab to get into that 3.5% range. Now, that is a lot. So we're not normally going to spill 150 liters. You may, however, spill 10 liters, and then if a spark comes near to it, in the vicinity of it, it'll ignite. But if those vapors are allowed to dissipate, you'll quickly get below the lower flammable limit. So these are a couple of things you can put together and say, is something dangerous? And for hand sanitizer, it's kind of amusing, but in many instances, it might be a dangerous liquid in a chemical store or in a production line, and we can assess, could we potentially get an explosion of this? The risk with hand sanitizers for smokers. For instance, if you are smoking and you do hand sanitize, then you could be in trouble quite quickly, because then you have an ignition source that could cause your hands to catch fire. Now, let's move on to the next topic, wildland fires. You look around the world and you will regularly find in the news issues about wildland fires and cities, towns, suburbs, rural areas being affected. Pictures like this, where an entire suburb is being decimated in California or Spain, even in Russia, Canada, all over the world, these fires are happening. Now, are they going to happen to us? Is this something we here in South Africa and the rest of Africa are going to need to deal with? The problem is, yes, very, very, very much so. Fuel loads, as in how much fuel is available for to be burnt, across the country, often allowed, and across the continent. Climate change is leading to longer periods of drought, reduced rain. So we have all the ingredients needed for mega fires, large fires that can devastate huge areas and wipe out lots of homes, communities. So let's have a look at how wildfires spread. Well, there's a couple of main mechanisms: convection and radiation. So in convection is the hot gases rising. So you've got a bush or tree burning, hot gases rise. Then you've got radiation. That's electromagnetic radiation that radiates over a distance, and that can cause something to be ignited at a distance. Now, then you also have the ignition mode that most people don't realize, and is actually the most dangerous in a wildfire normally. Flaming embers, otherwise known as firebrands or spotting. When a tree burns and there's a big wind blowing behind it, little pieces of bark, twig, leaves get blown. And now you can imagine hundreds of trees burning all at once, and those small pieces rain down distances in front, causing spot fires to develop, and then it can cause the wildfire to jump distances and then land on your patio and just find a pile of leaves under your patio. Land in your gutters and find some leaves you haven't cleared out. Land in, and touch the mop next to your back door and cause the mop to catch fire and then it to spread to your home. So those flaming brands are key and very dangerous, and most people don't realize they are there, and they don't realize they dominate fire ignitions and home losses in these big disasters. Once homes do ignite, however, then you have structure to structure ignition progressing through. So you now are number 5 in the suburb. So there are 4 lines of homes ahead of you. So you think, I've got lots of other homes that'll protect me. Well, the bad news is, if they are easily ignitable, they ignite and they spread it to the next home, to the next home, and you actually could get burnt through them. A home becomes fuel when it burns. And then it itself, as it burns, sprays embers and flames onto the adjacent homes. And that you will see in big wildland fire disasters, that fires can spread many rows of homes into a suburb. Now, when it comes to ignition of homes and wildland fire disasters, people often speak about as a river of fire and an uncontrollable force, but it's actually not. The fire still behaves according to the same physics, the same principles we discussed earlier. Here you can see a picture from Knysna. Now, where you are looking, there used to be a home. If you look above, you'll see the tree next door. Now, the top of that tree is green. It didn't even get hot enough for the tops of those leaves to be damaged. The house next to it is still intact. And even if you look at the staircase on the right-hand side, you'll see some of the staircase hasn't even been charred. See, it wasn't a river of fire that just came through. It was embers, flames, radiation that caused something to ignite, and then it spread through the house, the barn, the whatever structure it is, the trees, and then burnt down and moved on. But if you get a certain distance away from the flames, temperatures drop, radiation fluxes drop, and things will not even char or burn. So we've always got to have a look at the physics in the background of when will a home burn. And often it's, as I said, those flaming brands landing on the most easily ignitable items, and it's often the bushes around your homes. Now, let's have a look at the Knysna fire disaster. This was one of South Africa's biggest disasters ever in terms of fire, in terms of monetary loss, homes destroyed, deployment of firefighters. And what many people don't realize, there was actually 3 different fires, well, definitely 2, probably 3 ignitions that came together. We have what's called the Kruisfontein fire at about 3:30 in the morning on the 7th of June. That was ignited. There was also the Elandskraal fire. That had actually been burning for many weeks, and the CSIR did some very interesting satellite work tracking it. And there was a lightning strike, smoldering fire in the undergrowth, very slowly charring away from weeks on end, and then the wind changed on the day, pushed in it, and caused a flare-up. And the Elandskraal has been a lot of controversy about. But once it got going, it pushed all the way through Knysna and then joined up with the Kruisfontein fire and ended up in Plettenberg Bay ultimately. And this is quite large distances this fire covered. Then there was also a 3rd ignition reported and reported by other investigators working on the project. Now, we had spot fires up to 2.6 kilometers ahead of the fire front, and I'll show you these now. So on your screen, you'll see an image of one of the suburbs that was decimated. All the red dots are homes that were destroyed. So you can see 4, 5 lines, 7 lines of homes were destroyed, almost 100% destruction in some areas. The fire would burn through the vegetation, then jump through ember ignition, then ignite a home and spread through structure ignition, and progressively just move through the suburb, wiping out homes as it went. As I said, almost 1,000 formal homes destroyed, billions of rands worth of damage, and this will happen again. It's just a matter of time. Western Cape, Limpopo, various other places around, we are going to see more of these. This is not the last Nisa fire. If we have a look at the homes that were destroyed, the top table is the fire spread mechanism. Was it burned through the vegetation, or did it burn through the vegetation but it jumped at some stage, or was it had to jump a long way? It was ember ignition. Ember ignition can always happen, and then it's just ember ignition on its own, or ember and something else, or there was structure to structure. And then the bottom is how much vegetation people had around their homes. The main thing to take away, that of all the homes destroyed, almost 75% of homes had vegetation around them, thick vegetation. There was a pathway for the fire up to the people's front door. And it's nice to live amongst vegetation. Many of those homes were very beautiful and had lovely, lush trees and bushes around them. But when a drought comes, the trees and bushes turn into fuel, and your garden is probably more likely to govern your chance of survival in a fire than whether your home is made from timber or brick. We automatically think, oh, a timber home's going to burn down, a brick one won't. Brick is less combustible and probably to some degree safer. However, it's more probable that it's the vegetation around your home and even the leaves in your gutters that may cause your home to survive or not. So, can fires jump? As I was mentioning earlier, in this fire, it jumped the Knysna heads. If you look, depending on exactly where the embers came from, it was probably between 800 and 1,000 meters it covered at one stage. So if you were living on the right-hand side of this photo, you would have thought the fire would never get to you. I mean, there's an entire lagoon and sort of rocky clefts between you, but yep, jumped straight across, strong, very, very strong winds blowing, blew small embers, and you just need 1 or 2 or 5 just to land at the wrong point, and then the fire continues and it spreads through. There was another time, picked up 2.6 kilometer jump, as I mentioned earlier, and the satellite overpass was at just the right time, and they could see where the fire was burning, and suddenly a little spot fire popping up, and it could only have been blown across from across indigenous forest, which was less ignitable, and then it ignited a forest on the far side. And so we often have fire breaks. We have these 20 meter or 40 meter wide strips we call fire breaks. Now, that's actually a terrible name. They are not fire breaks. They are useful to get crews in to fight the fire, and in low wind conditions they might stop, but in high wind conditions they do not stop a fire. A fire break doesn't break the fire. It may slow it down a little bit, maybe in low wind conditions stop it, but it isn't the be-all and end-all. It's not going to protect you in high wind conditions, especially when there's lots of spotting and branding about. So which homes survived? Those homes with low vegetation. Those homes with limited combustible material within a few meters of their homes. And you have what's called the home ignition zone, and a lot of work being put into preparedness. And if you can prepare the few meters around your home with very low combustible, limited material, and then the meters progressively going by that you allow yourself a little more and a little bit more combustible material, that will probably be the reason your home survives. If a big fire comes through, it's what you do around the few meters in your home that may govern whether your lovely holiday house in Plett or wherever it is on the coast burns down or not. So let's continue on looking at another concept. In fire safety, we often want to keep homes safe, and there are many new innovations coming on the market and many different products, recycling initiatives. EcoBricks is one of them, and it's great that people are supporting recycling. And EcoBricks, you basically take a 2-liter Coke bottle, you fill it with non-recyclables, and you build a bench or a home or a school out of it. But Just a couple of things. The engineer and the fire engineer need to work together there. If this is a standalone house, a distance from anywhere, and if it burns down, it's not that serious, that might be okay. But just remember, what's plastic? Plastic's derived from oil. Plastic has almost the same energy content as petrol and diesel. You are basically putting a form of hydrocarbon fuel in your wall. You might as well put a couple of thousand small packets of petrol in your wall. That's virtually the energy content you add when you add these materials. So it is good to recycle. I'm not saying you shouldn't do this altogether, but we should be very careful in terms of keeping things safe. And you can imagine when they burn, they're going to burn beautifully. So for instance, in Guatemala, there's over 100 schools that have been built by one NGO. There are hundreds of homes, but the question is, are they fire safe? Do we want to build schools out of these materials? And this is where then fire scientists and engineers get involved, say, what is safe and how do we even assess it? Because this is not conventional. So this is some research by one of our students, Zara Sander, and Aidan Buerter contributing as well. You have walls where you put the eco bricks in and we plastered them and then we exposed them to fire conditions. What is very key is, well, A, the bricks will burn if the fire gets to them. B, that plaster layer in front is pivotal. If the fire gets through the plaster, then items ignite. You can have flaming and then they will flame for a long period of time. And you can imagine a couple of hundred little flamethrowers coming from a wall if the wall fails. However, if we put plaster on, at least we have an insulating layer that can protect them. And then minimum of about 40 mils, we're seeing for the requirements. So there is more work needed to go to be categorical. But this just highlights the interesting things that you may come up against where fire science and fire safety forms part of other problems in terms of poverty alleviation and the likes. So are we creating safe homes? Well, it depends. If we just have exposed eco-bricks, they can burn beautifully. If we clad them away, we may have some level of resistance against fire. At least they're not immediately exposed. So, other interesting things. Informal settlements are a major challenge from fire safety. Pretty much everything that you have in a settlement, from a fire safety perspective, shouldn't be there. You have dense homes, large amounts of ignition sources, small distances between homes, combustible homes, etc. So many different solutions have been proposed. One of them that got attention not long ago was fire retardant paints. So you'd go in and paint the homes with the fire retardant paint to protect it. And then the next fire that comes through, the paint would protect the home. So let's now apply our knowledge to this and to see how it would work. And just as a background, just to see how fast these settlements develop, this is just south of the Cape Town International Airport. That's 2014. In 6 months, hey, there's an entire settlement, and then it progresses to densify. So no bulk infrastructure, limited formal allocation of sites and areas, so dense homes on top of each other. As much as our interest in the aspect of informal settlements, fire safety is technical, it also goes beyond that. When I was a student, spent about 4 years working with kids from a burn survivor home. Would pick them up every Sunday, take them to church, and it's amazing when you see kids who've lost arms and eyes and been severely damaged by fires, because we can see the numbers of fires, but it's just a number. But when you see a child who is having skin grafts and missing an arm because of a fire, it brings it home just how important this area of work is for our culture, or our society to address. And to me, kindness shown to the poor is an act of worship, as the Bible says. So I think it's really an area we can make a difference. Here's an experiment. 20 full-scale homes ignited. The first row ignited at 0 minutes. After about a minute, it had spread to the second line of dwellings. So now we've got about 8 homes on fire. The fire continues to spread now. The wind is pushing from bottom left to top right at about 15 to 25 kilometers an hour, so it's a lot slower than you can get in Cape Town with the southeaster. Then the third line of homes, full-size homes, are ignited about 3 minutes. At roughly about 4 minutes, it reaches the fourth line of dwellings who are ignited. And then, give or take about 5 minutes, we have 20 homes on fire. The fire line pushed straight through 4 lines of homes, 20 homes on fire. Now, often people phone the wrong number, may not even phone. The fire department may be a distance away. It may take 5 or 10 minutes or 15 minutes for the fire department even to get there. And here already at 6-7 minutes, there's not a lot left standing. And you'll see the experiment soon speeded up. So we did this to study how do fires spread, and if we understand how fires spread, how can we stop them from spreading, and how can we evaluate when product ABC and company DEF comes to the mayor and says, Mayor, we've got a great solution, use our product, our fire suppression paint, whatever system they've got. Let's now have a look at how these homes ignite. And you're going to see a side view now as the fire spreads from dwelling to dwelling. A couple of things, key things to notice. Notice the very long flames pushing up and across. They will push up against a home and find any opening and ignite what's there inside. So if you have readily ignitable curtains or linings or cardboard or paper that people have shoved into holes, it'll find those, it'll ignite those, and then cause the rest of the home to burn and then spread and spread and spread and spread. So that is key. Those ignitable linings and the flames pushing in make a big difference. So now let's come back now to see how this might play out on a larger scale there. Rather than 20 homes, let's see how it affects 2,000. So this is Imizamo Yetu, introduced earlier. The fire started at the star there shown, and within the first sort of 7.5 hours, about 1 home per minute burnt down. There were major challenges with access, hose lines being cut as residents try to save their own dwellings, understandably so, cut lines to redirect water to save their burning dwellings, new lines being run, delay in the fire department being called out. The residents will say, the fire department took 45 minutes to arrive. I've actually heard a resident say this, but the log showed 3 minutes. It just took a while. They probably were phoning the wrong number, various other things. So the fire department got their set up, but very difficult fighting for the first many hours as it spread through this dense settlement. Now, then what happened? It hit a line of eucalyptus, blue gum trees, and then all hell broke loose, basically. Then about 9 homes a minute burnt down for the next hour and a half. And just push, and this is burning downhill. Normally fires burn faster uphill, but the wind was pushing it down here. 9 homes a minute with firebrands and all sorts of things raining down, and absolutely decimated this area. Now, any paint, etc., is not going to do very much. It's just, there was just fires everywhere. Fire department, large deployment of personnel, even there were helicopters fighting this, and it took them hours to get it. And then they eventually slowed it down, so for the next 2 hours, about 4 homes a minute, and then the final at about just 13 to 14 hours after ignition, they finally brought it under control. So let's start saying now, would a paint help this process? Here you can see an intumescent paint. This is a fire retardant paint. You heat it up and it expands. So there's a chemical reaction which forms a char layer. And that thick layer protects the material underneath. So the char is now a thick layer of sort of foamed material, and then it means that the underlying substrate does not get too hot. Now let's think, if we put this on a home, an informal home, a shack, would it prevent that home from igniting? Well, these products are designed to protect the substrate. It's designed to protect structural steel columns in a high-rise building or industrial process and the likes. It's not designed to prevent ignition and close gaps. We are trying to prevent fire spread. We're trying to prevent ignition, not to protect a substrate. And if you have a look at this diagram, there are just 3 things I want to point out. Ignition occurs by flame impingement, long flames onto our dwelling. Branding, small brands landing down, or radiation across a distance. Flames will find a hole, and the hole is not protected with paint. So the flames will slip in, ignite the dwelling, and the dwelling will burn down. So we're not addressing the home at the weak point. And even if we fire stop the openings, you always have a door and a window where the fire can come through. So it's not as easy as you think, just stopping these fires from coming through. That's why many of the interventions are just not suitable. So that just highlights some aspects to think about when you're evaluating what looks to be a very good proposal, but when it comes down to the physics of ignition, what are you trying to do? Are you actually trying to prevent readily ignitable materials from catching fire and being exposed to flames, or then stop the flames from getting to it. Don't stop the flames from getting to the underlying steel sheeting, the galvanized iron. So, in terms of dealing with informal settlements, I could talk about this topic all day. We've published a book, a free book on the topic, quite extensive, sponsored by Department of Human Settlements, Western Cape, and Lloyd's Register Foundation, so you can go download a copy here, and it goes through a wide variety of discussions on all sorts of topics. So, what next? I've discussed through science and physics and ignition and burning things down and various items. So, this has just been giving you an overview of fire safety engineering through looking at some interesting topics. So hopefully you've learned something moving away, but in terms of our continent, we've got a lot of work to do. Fire safety is lagging behind the developed world significantly, and we need a holistic response. We've written a paper on this work, but the main point is we need a holistic response from multiple levels, from codes to enforcement to engineering training through government intervention and everything in between. So, as Africa Burns, what do? There's a significant need for educational programs in fire safety engineering to keep our continent safe. We lack tertiary institutions offering formal fire training as they do in the developed world to be fire engineers. You have these creatures called fire engineers that design systems to keep buildings, industrial process safe, and we badly need them to be involved in all aspects of our economy. Now, quality of fire engineering services is often limited by lack of technical competencies. We have people who call themselves fire engineers in this country at the moment. Often they lack the technical training to provide useful solutions, and the insurers are picking up and are very worried that their interests are not being looked after by our engineers or so-called engineers. Now, our fire incident statistics are getting worse rather than better, so we can see we're losing the battle. There's a lot that needs to be done. Understanding we're in a developing nation, there's a lot of problems. We don't have lots of resources. We've got growing informal settlements, growing poverty. And this, though, forms a part of the bigger picture. As our economy uplifts, our fire safety will be uplifted, but we need our engineers there as well. So, fire departments often lack the resources and training, and there's a lot of things that can be done to build, especially certain areas of the country, the fire departments needing a lot of upliftment. Fire affects everyone. Don't think this doesn't affect you and me. But working together, we can make our continent safer. If the developed world has done it over 100, 200, 300 years, why can't we? So, just some closing thoughts. We are going to see wildland fires. We are going to see informal settlement fires. We are going to see power plant challenges. But working together, we can move forward. We can provide the engineers this continent needs. We can make a difference. And hopefully, you've also learned now about your car not igniting and various other things. And with that, I'm going to bring this talk to a conclusion, and we'll move over to a time of questions now. Thank you.